Okay, here we have a prelude to section 4.2, which is on implicit differentiation. And you're going to see some notation if you go through problems that'll be confusing to you, I believe, because we don't have an understanding of implicit differentiation until we really realize that it is utilizing the chain rule. And that's why section 4.1 was about the chain rule, so it could lead into implicit differentiation. So chain rule, one of the ways it is presented, and this is my favorite way, is it says if we are finding the derivative of a composite function, we have an inside function, we have an outside function, f. If we're finding that derivative, we take the derivative of the outside function of the inside function times the inside function's derivative. So that is chain rule. And it's not going to seem like that's what we're doing right away in product rule if you just look at some examples, but I want to explain through this why implicit differentiation utilizes chain rule. So we will use implicit differentiation in a number of cases. Sometimes we have curves that aren't even functions, such as circles or ellipses or anything that would not pass the vertical line test. Those are good implicit differentiation type equations. And other times that we might do that we might use implicit differentiation is if we actually have a function and it's just very, very difficult to solve for y. We can differentiate implicitly. The differentiation we've been using up to this point is explicit. Okay, so I'm going to jump right into a problem here. Let's go ahead and say, what if we had 3y squared x cubed minus y to the fourth x equals 7. And we need to find a slope formula for whatever that curve happens to look like. So we would go ahead and take the derivative. Now it's important to note that this is a product. It's a function on y times a function on x, so we're going to use product rule here. Likewise, this is a product. We're going to use product rule here. So we have to find the derivative of this. Now, y squared does not act like a constant. If I'm taking the derivative with respect to x, I can't just bring the 3 out in front and make that 9y squared x to the second, because y is not a constant value. So that's where we differentiate implicitly. So I'm going to set this one up. We're going to take the derivative of both sides. So I'm just going to use that little tag for derivative of both sides. And because it's product rule, we get the plain old first term the way it was times the derivative of the second term, 3x squared. Easy enough. Plus, now we take the derivative, I'm just going to write it this way, 3y squared's derivative times the just plain second term, or second factor, minus all of, another product rule, derivative of the first term. I'm just going to write that as y to the fourth's derivative times just plain second factor, I think I said term, I mean factor, plus the just plain first factor times the derivative of the second. Okay, here's where the chain rule part comes in. Okay, so we've got, this one's simple enough. Here we've got 9 x squared y or y squared x. I'm going to go x squared y, no real x squared y squared, no real reason there. Now I need this guy's derivative. This guy's derivative. We need to realize that if we solve this equation for y, we would have y is a function of x. If I could get y alone, maybe I could. But if I got y alone, y would be a function of x. So this is like a function of x inside another function. So we want the outside derivative, 2 times 3, 6, of the inside function y. You don't need the parentheses, but I'm just trying to emphasize to the first. But that's not, see, y is not x. We're not taking the derivative with respect to y. We're taking derivative with respect to x. So it's the outside derivative, 6, of the inside function y to the first, times the inside derivative, and the inside derivative is dy dx. It's derivative of y with respect to x. Okay, we multiply that by x cubed. We get minus, I think I'll distribute along the way here. Now, this is y is a function of x. It's not x. So this is not just 4y cubed. It's the outside derivative, 4 of the inside function to the third, 4 something to the third, times the inside derivative. So what we're learning here is anytime we implicitly take the derivative with respect to x of a factor or a term that has a y in it, we're going to end up with a dy dx. That's the chain rule part. We have to take the derivative of this function after as part of the chain rule, just like we do right here. Okay, then I've got a minus y to the fourth. The derivative of 7 is 0, so equals 0. Okay, next thing we want to do is we want to group our terms that have dy dx in them, here and here. So I'm going to leave those on the left side, maybe clean them up a little bit here. I've got a 6, this whole term. I've got a 6, I've got an x cubed, I've got a y, and I've got a dy dx. That's why it gets to stay over here. Minus 4y cubed dy dx equals, I'm going to add y to the fourth to the other side. I'm going to subtract 9x squared y squared, truthfully on both sides. And now I want to solve for dy dx. I get dy dx times 6x cubed y minus 4y cubed, factor it out, equals y to the fourth minus 9x squared y squared. And if I divide, I get dy dx, here's the big payoff, equals y to the fourth minus 9x squared y squared, all on 6x cubed y minus 4y cubed. And then we notice we can cancel a factor of y. Every one of these terms has a factor of y. So y cubed minus 9x squared y on 6x cubed minus 4y squared. And I can't cancel anything else. So there is our final implicitly differentiated slope formula. Therefore, now we could even think of writing this as f prime of xy, f prime being slope formula, but we're used to f prime of x. Now if I have an ordered pair that's on the curve, let's say we knew that 3, 2 was on this curve, I could put 3 in for x, 2 in for y, and find the slope at that point. So if we're looking for a rate of change on a tough function to solve for y, implicit differentiation can be our friend. Okay, with that introduction, that really does a lot of the explanation for what we're doing here, or for these first couple of rules, and we're going to jump right into the differentiation here, and I'm going to go through some of these pretty quickly here, but you have the ability to pause, so let me get zoomed in here just a little bit here so you can see it easier at home. Okay, so implicit differentiation, again, very similar to the one we just did. Let's see how we do on this. I want x squared, this is product rule, times the derivative of y with respect to x, well that's just dy dx, plus the derivative of the first factor, 2x, times the plain old second factor, y. Now product rule, this guy, plus all of plain old x times derivative of y squared with respect to x. So that is times 2y to the first times the inside function y's derivative, dy dx. Plus the derivative of the first function, the first function, x, is 1 times plain old y squared. Equals derivative of 6, 0. Didn't matter what 6 was. 6 could be a million. It's still 0. Okay, group our dy dx's, and I get x squared dy dx plus 2xy dy dx equals subtract 2xy, subtract y squared, and now if I factor out dy dx, if I factor that guy out, we will just get, we'll be left with this and that, which I'm going to divide across to the other side. So that becomes negative 2xy minus y squared over x squared plus 2xy. Nothing cancels, and we got it. All right, hope that makes sense to you. Let's start moving through these.
Static area will be locked down in 10 minutes. Access to hallways will be for authorized personnel only. Thank you.
Okay, sorry for that brief interruption. So I want to, we can take this plus or minus square root of both sides and work with two different functions and to try to determine, are we dealing with the top or the bottom half of some curve. But I'm going to go ahead and derivate this implicitly. So the derivative of y squared with respect to x is 2y to the first times that inside function of x's derivative, dy dx, equals low d high minus high. Derivative of low is 1, all on the square of the thing below. Low d high minus high d low on the square of the thing below. So we got that. So this becomes 2y dy dx equals, let's see, I get an x and I get a minus x. X's cancel. I get a 1. I get a positive 1 times 1. That is 2 on x plus 1 squared. If I divide both sides by 2y, I end up with dy dx equals, when I divide by 2, the 2's cancel. I end up with 1 on, divide by y, x plus 1 squared. Okay, hope this is making sense to you. This would be a time where if I was teaching the class live right now, I'd say, go ahead and give this guy a try. But let's run through this. I'm going to take the derivative of both sides. Now I understand it's easy to solve this for y. I'd get y equals tangent inverse of x, and then I find the derivative of tangent inverse. But if I don't know how to find derivative of tangent inverse, then I'm going to go ahead and implicitly derive this. So derivative of x is 1. Derivative of tangent, now again, there's an inside function of x here. Derivative of tangent is secant squared of the inside function times the inside derivative, which is just dy dx. Therefore, dy dx is divide away secant squared, 1 on secant squared of y, or dy dx, reciprocal of secant is cosine, so cosine squared of y. So pretty cool. If I want to find any slope of tangent, when we have x equals tangent y, I can just put a y value in here. I get cosine squared of y. Okay, similar problem because we got that tangent in there, but here's what we got to be alert to. This is going to be a product rule. So derivative, both sides, derivative of x is 1, derivative of tangent is secant squared of what? Of the inside function, times the inside derivative, xy's derivative, equals derivative of 0, 0. So we get 1 plus secant squared xy. Here again is another product rule. So that's times all of the first function x times derivative of second dy dx plus the derivative of the first function 1 times the just plain second function y equals 0. And now you might want to distribute here, but I know what I'm looking for. This is what I refer to as the hot variable. I want to solve for it. I can start solving for it right now. In fact, I could peel away a 1 by subtracting it, and I could peel away the secant squared xy by dividing it away. And I could do more steps than that, but I'm going to stop at that one for right now. I'm left with x dy dx plus y. If I'm solving for dy dx, the first thing I would do is I would subtract y. Now, when I subtract y, I could also, before I did that, I guess this would be the first thing I do. I'd take a look at this. I can call this negative cosine squared xy, just like we did on the previous problem. Then subtract y, and then to get dy dx alone, last thing I have to do is divide by x. Okay, so Not too bad, just different. So hopefully the biggie is you're catching on, understanding the whole, when we take a derivative with a y in there, we're going to end up with a dy dx. Hopefully you're understanding the chain rule portion of that. Let's take a look at a couple more problems here. Find dy dx and find the slopes. Kind of a cool problem here. Here we have a curve we should be pretty familiar with. This guy is a circle. Let's see if I can do this circle justice. Actually, that's pretty good for me. With center 0, 0 and radius square root of 13. And they're saying somewhere on that curve, negative 2, 3 is on it. Let's see, negative 2 squared 4 plus 3 squared 9, 4 plus 9, 13. So 2, 3, negative 2, 3 would be somewhere shorter here. Let's see, root 13, a little bit more than 3. Negative 2, 3 would be higher than it is wide, or out to the left. And therefore, that really tells me, if I think about that, that tangent line slope definitely is positive. And I would expect if I was out here at the same value and have 45, 45, then my slope would be 1. So I believe this is positive and less than 1. Let's take a look. Take the derivative of both sides. So I get 2x. Derivative of y squared is 2y to the first times dy dx. Because that is chain rule. That is a function of x inside of here. So 2 times the function of x to the first times the derivative of the function of x, dy dx, equals derivative of 13, 0. Let's solve this for dy dx. dy dx equals subtract 2x, divide 2y, and I get dy dx is negative x on y. And we're supposed to find the slope here. And I mentioned earlier, we could think of this as a slope formula, f prime of xy. I want f prime of negative 2, 3, so that is the opposite of negative 2, the opposite of x, negative 2 on y, 3, or 2/3. And of course, where might we go from here? This is just kind of an appendage. We might be asked to find the tangent at that point. So the equation of the tangent. So that would be y minus the y coordinate 3 equals slope 2/3 times x minus the x coordinate, x plus 2. And slope-intercept form or not, we could certainly work to that if we needed. Or we might be asked to find the equation of the normal being perpendicular to that. So the equation of the normal, of course, then would just be y minus 3 equals perpendicular to a slope of 2/3 is a slope of negative 3/2, but still passing through the point negative 2, 3. Okay, this would be a really good time for you to pause the video and work ahead of me. Very similar. Okay, we're going to take the derivative of this. We're going to get 2 times the derivative of x minus 1 to the first times the derivative of x, but that's just 1, plus 2 times the derivative, or excuse me, 2 times y minus 1 to the first times the derivative of y minus 1, well, that is the derivative of y with respect to x. Derivative of 1 is 0. Equals derivative of 13, of course, is 0. So you might want to start distributing here, but again, for me, I'm not looking at what can I do, I'm looking at what should I do, and what I should do is get dy dx alone. So dy dx, I would subtract 2 times x minus 1 and divide 2 times y minus 1, and I've got it alone. So dy dx is 2's cancel, distribute the negative, negative x plus 1 on y minus 1. And we want f prime of the point 3, 4. Let's see if we can predict. By the way, it didn't come back to that, but look how our prediction was last time. We felt like the slope would be positive, and we felt like it would be less than 1. Let's take a look at this prediction. So I'm at 1, 1, and we want to point at 3, 4, somewhere up in here that's on the circle. It's over 3, up 4, so it's up more. The further it gets up, the flatter the tangent line gets. So I believe this one is going to be less than or closer to 0 than -1, but negative. Now let's take a look. So f prime 3, 4 would be negative the x value, 3, or the opposite of the x value, plus 1, all on 4 minus 1, and I get negative 2/3. And again, we could go through the whole tangent line argument or normal line argument that we went through in the prior problem. Okay, let's continue. I got a little bit of time here. Find where the slope of the curve is defined. Find where it's defined. Well, if I'm going to find where the slope is defined, I'd like to get my slope formula or my derivative. Again, we've got product rule. We've got product rule. We've got a minus that we better distribute when we run through the product rule. So, first product rule. I need the just plain first factor, x squared times derivative of the second, dy dx, plus the derivative of the first, 2x times the just plain second, y, minus all of the just plain first, x, times derivative of the second, that's times 2y to the first times dy dx. We're catching on to this. Plus derivative of the first 1 times the just plain second, y squared, equals derivative of 4, 0. All right, let's distribute x squared dy dx minus 2xy minus 2xy dy dx, but minus times positive, minus y squared. Let's quit making that mistake. Equals 0. I'm going to group my y's, my dy dx's, because I only want one of them, and I'm going to factor out a dy dx. Dy dx, I don't know why I did that, excuse me. Dy dx factored out times, I'm left with an x squared and a minus 2xy from those, equals, I'm going to add. Why did this become a minus 2xy? Ooh, I'm glad I caught that. I'll bet you were waiting to get me on that one. I'm going to add a y squared across, and I'm going to subtract across a 2xy. That could be in the other order. So dy dx is y squared minus 2xy on x squared minus 2xy. Don't you dare cancel those 2xy's. And now the question says, find where the slope of the curve is defined. Now, understand, this curve, I'm not saying this is what the curve is, but this curve could exist and look something like that. I don't know. I'd have to play around with it. Maybe that curve looks like this. We're supposed to find the slope, but we're finding where the slope of the curve is defined. So it wouldn't be defined at all until we got to the curve. So we have to make sure to word this carefully when we're done. But when is the slope undefined? This is the slope. The slope is undefined when x squared, my denominator, minus 2xy equals 0. Well, a quick factoring here. X times x minus 2y equals 0 when x equals 0, or when x equals 2y. That's when it's undefined. Now, good chance that this will be solved for y. Y equals 1/2 x. So we would say that the curve, the slope of the curve, is defined on the curve, on the domain of the curve, when x is not equal to 0, and you could put x is not equal to 2y, and y does not equal 1/2 x. Sorry, I had that cut off for a little bit. So we've got to be kind of careful. We don't want to just say, oh, the slope's not defined at 0 and when x is 0 and when y equals 1/2 x. We have to be talking about that domain. We have to be talking about that domain. Again, this is not the graph of this function, but perhaps this function doesn't exist everywhere. In fact, very likely it's not even a function. Okay, good time to give one a try on your own here. If you want to pause the video, we'll see you back. But I'm going to start it right now. We're going to find our slope formula. So this is derivative 3x squared plus derivative 3y squared dy dx equals product rule. Don't let it get you. First times derivative of second dy dx is the derivative of the second factor. Plus derivative of first 1 times the just plain second y. Group our dy dx's. I'm going to leave 3y squared dy dx over here. I'm going to subtract x dy dx on both sides. I'm going to leave y over here. I'm going to subtract 3x squared across. And now let's factor out a dy dx. And I get 3y squared minus x equals y minus 3x squared, and divide dy dx is y minus 3x squared on 3y squared minus x. I hope you tried that on your own. Hope you had some success with that. So what do we know? We know that the slope is defined provided x does not equal 3y squared. If we solve that for y, we could say y cannot equal divide 3 plus or minus square root of. So we would say the slope, in fact, what if we said this? The slope on the curve, is defined when x does not equal 3y squared, or when y does not equal plus or minus. By saying on the curve there, we're taking anything that's off the curve, because clearly if we had this situation again, the slope of this, you can't call it a function, the slope of this curve is clearly not defined over in here. Okay, let's run through this. Find the lines that are tangent. Oh, we are so ready for this. We're going to find the tangent of the normal. We warmed up. Again, you could probably pause this right now and give this a shot. Derivative 12x, that was a breeze, plus product rule. I'm going to call this first factor, second factor. The just plain first factor times the derivative of the second, dy dx, plus the derivative of the first, 3, if it's 3x, 3 times the just plain second y, plus derivative of 2y squared, 4y dy dx, plus derivative of 17y, 17 dy dx, plus derivative of negative 6, 0, equals derivative of 0, 0, equals 0. Group our dy dx's. 3x dy dx stays, plus 17 dy dx stays, 12x goes, minus 12x. Oh, we got another dy dx here. Did I do that right? 17 dy, yep, I sure did. So we got another dy dx, my fault on that. I've got a 4y dy dx also here. And what goes? 12x goes, and I subtract 3y as well on both sides. Factor out dy dx, I get a 4y, a plus 3x, you might have these in a different order, a plus 17 equals negative 12x minus 3y, and dy dx equals negative 12x minus 3y on 4y plus 3x plus 17. That is our slope formula in terms of xy. And I want my slope at the point, ordered pair, negative 1, 0. They're telling me that must be on here. I'm not going to go through that. I'm going to take their word for it. Negative 1, 0. So that is negative 12 times negative 1 minus 3 times 0 over 4 times 0 plus 3 times negative 1 plus 17. Or let's see, I get 12 and 0, 12. Down here I get negative 3 and 17, 14. I get 6/7. So we got a slope of 6/7. We've got a point of negative 1, 0. Our tangent, equation of the tangent line is y minus the y coordinate 0 equals slope 6/7 times x minus the x coordinate, x plus 1. You could certainly easily distribute through that. We're practically in slope-intercept form already. And our normal, just perpendicular. Boy, if you get the tangent right, you can't miss the normal. Y equals negative 7/6 times x plus 1. Distribute at will. Okay, and just a little bit messier. Where some people get messed up on this, we see pi, it doesn't look at it as a number, and we think product rule this. But pi is just a number, so we can just treat this as a coefficient in front of sign. So this is going to be a product rule, though. Take our derivative. I get the just plain first function, 2x times derivative of y, dy dx. Plus, the derivative of the first is 2 times plain old second y. Then the derivative of this guy is easier than I thought at first, plus pi times cosine y, but dy dx equals derivative of 2 pi 0. So there we have it. Group our y's. I'm going to factor and group in the same step. Dy dx times 2x and times plus pi cosine y equals negative 2y, or dy dx equals negative 2y on 2x plus pi cosine y, and we are interested in what happens at 1 pi on 2. Okay, what I know for sure for my tangent line, I've got y minus pi on 2 equals something times x minus 1. So I need to put 1 in for x. So f prime of 1 pi on 2 is negative 2 times y value pi on 2 over 2 times 1 plus pi times cosine pi on 2. A little quick simplifying here. I get negative pi on 2 plus pi. Cosine of pi on 2. Maybe we should have that one memorized. But cosine of pi on 2, here's cosine. 2 pi, pi, here's pi on 2. It's 0. So plus 0 or negative pi on 2. There's our slope. Therefore, our normal line, there's our slope, negative pi on 2. So our normal line would be y minus pi on 2 equals equals positive 2 on pi times x minus 1. So there you have it. I hope that's helpful. Assignment, got some good problems to work on here. Make certain you're asking any questions if you have them. Thank you for your time.